that can be accommodated there. This is what the outsat looked like. The picture on your right, inside that volume, and that's a picture of what the actual plate. It's kind of a spider plate. It's a little hard to see there, but where it's pointing to the 15-inch bolt hole pattern, that's the actual plate itself, and the bolt accommodation system there. And like I say, the spacecraft gets loaded in that horizontal position at the launch site, and this whole thing gets taken out and mounted inside the interstage adapter, and we do a few remove before flight flags there, but we have been accommodating some propulsion units and things of that sort. So it is broadening the spectrum of things that we can host. Picture of the team that was working on that, some of the Cal Poly folks, the Naval Postgraduate School folks, the SRI folks. There was quite a collaboration of people involved with this thing. And the picture on your left shows the shaker table that was it was going through Vibe on. But that's how the plate comes to us. It gets put on this rotating platform, that's the one on the left, and gets rotated in the proper configuration so we can hoist it up and mount it to the vehicle. The C adapter platform is another one that we're using for hosted experiments. Primarily, it was built for a battery platform to go to GSO, but it can host experiments, mainly for non-separating type systems. There is a flat plate as opposed to an L plate configuration, but it can go up to 100 kilograms actually. But it was qual to 100 pounds mass per the Air Force specification. This is pictures of it being loaded in through a 5-meter fairing and attached. So it's kind of a little bit of a contortion process to get through the fairing access port, but that can be done even once the vehicle is stacked. ESPA ring, you're all familiar with that, I'm assuming. Moog CSA is here to present. They're going to present later on, I think this morning or this afternoon, tomorrow. So Joe Malley is here. He can defend that stuff. The ESPA ring adapter has been around for quite some time, and it's expanding its capability as well. This is originally designed for 181 kilograms, and there's an ESPA Grande he's going to talk about. This was STP-1, and it shows the stack configuration inside the 4-meter fairing. And this flew to a couple of different orbits. So we do have engine restart capability, so that can be accommodated. Typically, when we do these SmallSat LEO type missions, we're letting the primary go at a higher altitude because that's where they want to go, but we will descend to a lower altitude so that we can let the small sats go, and then they can perform their mission and then comb out after like a year or whatever to mitigate the orbital debris problem that we're all kind of restricted to. So it's an interesting process to do the mission design for these things. Another thing we've been working on is the ABC deck, or ADEC we call it. It's Aquila, it's the new name for it, but it's a platform that can sit inside of the C-rings. We always have to have a ring that we can lift the primary payload stack to put it onto the rocket. So this is using the internal volume of that ring stack, and once the primary payload is separated off, you have a clear hole that you can launch other payloads inside that 5-foot, 60-inch internal ring diameter up to 1,000 kilograms. There's flavors of that go up to 1,000 kilograms. So we've been looking at space telescopes that are as tall as 7 feet. Go in there, a variety of different applications. That's what the stack looks like, and I'm not going to dwell on it too much. This is the qualification for the heavy payload, the 1 kilogram system. It's being we started as a IRAD, but it's been taken over by the NRO, and they've gone through and finished CDR with this and gone through qualification testing. And looks like we're going to have a flight here in another 2 years on the heavy version. This is a picture of the qualification process that they were going through. This is the LRO L-Cross mission. Anyway, that's what LRO L-Cross. This was really an experiment, hosted experiment. They used the ESPA ring as part of the platform. They bolted everything onto that except for the one separating element, the camera sensor suite that deployed and followed in to the impactor that was like 4 minutes behind it. But so it was a very interesting experiment that they were able to do with a separating on the top. It did not separate on the bottom, but we did integrate on the bottom. Don't touch it. That one. Okay. All right. Let me get up out of there. Okay. I borrowed this chart from our Busick Propulsion folks from Boston. They have, talking about CubeSats, this is a 6U platform that we are entertaining the idea of being able to put that into a CubeSat deployer that would fit on an ESPA ring or on an ADEC adapter package that could fly to the moon as an ion propulsion system. It would go off of a GTO kind of a orbit and be able to deploy from a GTO and spiral out using that ion propulsion system that they've been developing. This is another package that we've been working on as a bus. The idea here is that with a fairly low power, in this case it's a 4 kilowatt electric propulsion system with a quad ion propulsion package. In this form, what we're looking at is not a xenon type propellant system, but we're looking at a more dense iodine solution that we get away from the heavy scuba tanks and use a very lightweight composite system. So we can fit all of the propulsion propellant inside the ESPA ring. We can put 4 ESPA packages on there. Propulsion system occupies 1 space, avionics on another space. The other 4 spaces are available. If this goes to interplanetary, you need a deep space network type antenna for a high gain antenna. So one of the platforms would occupy a high gain antenna. But even for a Mars mission, this could make it to Mars with a Earth escape disposal type injection from, let's say, a polar mission. So this could take either SmallSats or the 8 CubeSat deployer for P-pods to as far out as Mars in this case. Now I get asked a lot of different questions. Where can we go? How can we get there? And one of the questions that we were asked was, well, okay, if we wanted to start from a GSO position, how could we get there and how much could we carry? So if we take the Atlas configuration vehicle and we were allowed to add solids to that, we could deliver a primary payload that would go to GTO up to 19,000 and plus pounds, and then still carry from a GSO position a ride share of up to 2,200 pounds or 1,000 kilograms. And so the rationale is that we would be subtracting from the maximum payload GSO the accoutrements that are necessary for that, the mission kit to extend it to a GSO type mission. So that's what the B is those accoutrements that have to subtract from that maximum payload. But so it is possible to get to 1,000 kilograms up to GSO for releasing SmallSats or CubeSats. This is another rendition of that Lunar CubeSat ferry, where you have multiple CubeSats that could be carried. This going back to the xenon tanks, but like I said, we have a more advanced propulsion system that's available now. This is some of the performance and mass fraction and timeline data based on that 4 Busick BHT 1500 Hall effect thruster quad system. And so it gives you some of the transfer times that would be accommodated by this carrier. This is the Mars mission concept, being able to make it out to Mars. Again, this would be based on a Earth escape disposal from a polar orbit. We would release the primary payload in polar orbit and then do a burn to do Earth escape, and then release the carrier, which would then deploy its solar panels and make it out to Mars. And our studies show that it could make it to Mars given the right trajectories in about 2 years. The nice thing about this is that you would then have the high gain antenna available to support the CubeSats. So if you're doing that kind of a mission, it would be available to support the comlink back to a deep space network communication link there. We've also been doing experiments using this system with higher gain, higher wattage propulsion, and in this case up to 20 kilowatts. And so that shows some of the thrust versus ISP with those higher power systems. Now, how we would accommodate that, we're looking at stowed configurations. There's a variety of stowed configurations, but one of them that's kind of interesting. One of them is kind of interesting is being able to use the volume inside of a 5-meter fairing that's down alongside the body of the upper stage. So as you see here depicted, the ESPA ring is in the middle of the picture at the nose of the upper stage. Articulating booms would pass down through a CFLR deck that's a ring configuration that's 2 D rings that fit around the collar of the upper stage to hold out the 5-meter fairing. But if you pass those booms through that CFLR deck, you can take advantage of that 30 inches of volume that's between the Centaur body and the keep-out zone of the 5-meter fairing. So you got 30 inches of space there and 10 meters long to go along that body. So you can pack quite a bit of power, up to, we think, 100 kilowatts is not unreasonable to be able to stow in that kind of a configuration. That allows you to push a primary payload with that kind of power system with the propulsion package in the center of that ESPA ring. And again, this is the TDRS mission, a conceptualization of a Mars mission where the ESPA ring acts as a data relay system for a series of geostationary or Mars stationary deployments. So what can it do? Well, we can do fairly large missions. We can add solids up to 5 to get 1,000 1,000 pounds margin for each solid. So there is a lot of latitude to what we can do to support the launch of lunar or even interplanetary spacecrafts. We can help to broker the rideshare with the primary partners, and we need to work with the schedule and the milestones for that primary mission to integrate in that rideshare. There are opportunities that are presenting themselves, and this is an ongoing thing on out many years even beyond this chart. So there are opportunities that are available. The key is to get involved at the beginning of a mission campaign. That's very important to define the stack and not redo any of the integration that's involved with that. What's in work? We are doing ABC missions. There are NRO missions that are out there. They are integrating small CubeSats on those missions. We are also looking to reduce the cost of that ABC to make them more affordable and more provide more opportunities. We are working with integrators to provide a matched commercial rideshare with both government and commercial missions, trying to make this more routine and more affordable. And obviously, we're also working with the Galaxy or the Google Lunar X Prize participants for lunar exploration. So, in closing, we need to think in new ways of how we can do ride shares, both for lunar and Mars, interplanetary missions. Sometimes we need to invent new things, new tools, and sometimes we need to hammer that point home with a lot of folks. So with that, I'll entertain any questions.